All right, welcome to everyone who's attending both in person and on the Zoom live stream. It's my pleasure to introduce the first speaker of today's session, Jim Belk, coming from the University of Glasgow, talking to us about embeddings into finitely presented simple groups.
Thank you. And I'd like to thank the organizers for inviting me. So I'm going to be talking about a almost 50-year-old conjecture. This is the Boone-Higman conjecture. And the conjecture is that if you have a finitely generated group, then that group has solvable word problem if and only if it can be embedded into a finitely presented simple group. And this is almost 50 years old. It's completely open. And I stated the conjecture for finitely generated groups, but I do want to say it would suffice to prove this conjecture in the case where G is finitely presented. It's known that every finitely generated group with solvable word problem embeds into a finitely presented group with solvable word problem. So this is really a conjecture about finitely presented groups. And I don't have anything like a proof of this conjecture, but what I do want to talk about is some progress, which is of the form, there's all these finitely presented groups that people care about. And so you can ask, well, which of them can be embedded into finitely presented simple groups? And so there's been a lot of recent progress of the form taking groups of interest and embedding them into finitely presented simple groups. So what I'm going to talk about is first, I'm going to talk about what the motivation for this conjecture was, why Boone and Higman thought something like this might possibly be true, and then which groups at this point we know how to embed into finitely presented simple groups. And a lot of what I'm talking about today is joint work with my collaborators. This is Colin Blake at the University of St. Andrews, James Hyde, who's at the University of Copenhagen, Francesco Matucci at the University of Milan, and Matt Zaremski, he's at State University of New York at Albany. Okay, and so to understand where this Boone-Higman conjecture comes from, we should start with classical result. This is Higman's embedding theorem. And this is a theorem about countable group presentations. So you have a group presentation, and it has a countable set of generators, which can be finite or infinite, and a countable set of relations, which again can be finite or infinite. So a group presentation like that is said to be computable if there exists an algorithm that could output the list of relations as words in the generators. And so if a group has a computable presentation, then it's said to be a computably presented group. And there's some obvious examples of this. So any finitely presented group is going to be computably presented because there's an algorithm that lists a finite set of relations. A little bit less obviously, if you have a finitely generated subgroup of a finitely presented group, it's always computably presented. And the way that works is, so you have your finitely generated subgroup, so you can take each of your generators and write it as a word in the generators of your bigger group. And then you have an algorithm that outputs a list of relations in your bigger group. And what you can do is you can start computing all the possible consequences of those relations. And whenever you find a consequence that involves only the words that you had for your generating set for your subgroup, that's a relation in the subgroup. And in this way, you can find actually all the relations in the subgroup. And so that's an algorithm that outputs a computable presentation for the subgroup, so the subgroup is computably presented. And Higman's embedding theorem is that that's an if and only if. So if you have a finitely generated group, then the group is computably presented if and only if it embeds into a finitely presented group, right? And so the forward direction is the hard direction here, that if you have a computably presented group, that it can be embedded into a finitely presented group. And a few things I want to say about this theorem. So first off, this theorem has various consequences because various things are known to embed in computably presented groups. So for example, so it follows from this theorem that every countable abelian group embeds into a finitely presented group, because it's known that every countable abelian group embeds into a finitely generated computably presented group. This is kind of interesting. So Higman was for many years interested in finding explicit examples of such embedding. So Higman's proof is explicit, but if you wanted to find a finitely presented group that contains, for example, Q, the additive group of the rational numbers, and use Higman's proof, you get, I don't know, 100 generators and 100 relations, and it will be some enormous finitely presented group. And so it's a basic problem. Can we find a nice, explicit, natural example of a finitely presented group that contains Q? And the other thing to notice about Higman's embedding theorem is that it has the following form. It says that a group has a certain algorithmic property, in this case, having a computable presentation, if and only if it embeds into a certain kind of group. So Higman's embedding theorem raises the question of, are there other theorems of that kind? So if you have some other algorithmic property, is that equivalent to embedding in some class of groups? Okay, so that brings us to the Boone-Higman conjecture. And the Boone-Higman conjecture is, I think, largely motivated by the following observation. This observation was made by Richard Thompson in 1969 at a conference, and then it was later discovered that it had earlier been made by Kuznikov in a Russian language paper that hadn't seen wide circulation. But the observation is that, in fact, every finitely presented simple group has solvable word problem. And as I said, Thompson made this observation at a 1969 conference, and Higman and William Boone were both in the audience. And okay, so why is this true? So we have a finitely presented simple group, and we want a solution to the word problem. Well, if I give you a word, one thing that you can do is try to search for a proof that that word is the identity. You take the relations in your group and start deriving all consequences of those relations, and you see if you happen upon a proof that the word is the identity. You can do that in any group. And if the word is the identity, you'll find a proof of it that way. The hard part in most groups is sort of the other search, is finding if a word is not the identity, how do you get a proof that a word is not the identity? But in a simple group, if a word is not the identity, if you add the relation that the word is the identity, then the whole group collapses. So if you want to know that a word is not the identity, what you do is you start with the relations in the group together with the relation that that word is equal to 1, and you see if you can prove that all of the generators are the identity. And if you've done that, you will have shown that your word is not supposed to be the identity. And so the solution to the word problem is you run these two searches simultaneously. And so every finitely presented simple group has a solvable word problem. And Boone and Higman recognize this as being sort of a group theoretic analog of a basic observation in logic, which is that every complete theory with finitely many axioms is decidable. So a complete theory, of course, is an axiomatic theory, so that if you add any other axioms that don't already follow from the existing axioms, then the whole theory becomes contradictory. And so when you have a complete theory with finitely many axioms, and you have a statement, and you're trying to figure out whether it's true, you can, on the one hand, search for a proof that it's true. And then you can, on the other hand, assume the statement is true and see if you can derive a contradiction. And in which case that means the statement must have been false. Right? And so in this way, you can always decide whether a statement is true in a complete theory with finitely many axioms. And so there's sort of this analogy here between logic and group theory. And so a simple group is like a group theoretic analog of a complete axiomatic theory. Okay. And so based on Thompson's observation and this sort of analogy, and the Higman embedding theorem, they decided that this would be a reasonable thing to think. So perhaps a group has solvable word problem if and only if it embeds into a finitely presented simple group. By the way, finally generated subgroups of groups that have solvable word problem always also have solvable word problems. So, right, any finally generated group that embeds into a finally presented simple group is going to have solvable word problem. Okay, so they tried to prove this. Oh, right, by the way, it would be a corollary of this that in fact any countable abelian group would be embeddable into a finally presented simple group. So, you know, same question. So we don't need, you know, so it's hard even to embed Q into a finally presented group, but if this were true, Q would embed into a finally presented simple group. Okay, and they tried to prove this. They did not exactly succeed, but they proved the following partial result. They showed that a finally generated group has a solvable word problem if and only if it embeds into a computably presented simple group. And so that's the Boone-Higman theorem, and the conjecture is about getting from computably presented to, in fact, finally presented. I want to show you a little bit of how they did that. So they used a trick. So you have a finally generated group with solvable word problem. We want to embed this into a computably presented simple group. So we have group G. Group is simple. So simple is the same as saying that if you take the normal closure of any non-identity element, that will contain every other non-identity element. So you have this group G, and it has lots of pairs of non-identity elements that may not be in the normal closure of each other. But you can do this little trick. So given your group G and a pair of non-identity elements, you can make a group G prime that has this presentation here. And so what is this presentation? So we took G and then we added X, and that puts us in the free product of G with the infinite cyclic group. And here we've got U times U conjugated by X, and that's being conjugated by T equals U conjugated by X multiplied by V. So notice that if U and V are not the identity, then U times U conjugated by X is an infinite order element in this free product. And this U conjugated by X times V is also an infinite order element in this free product. And so what we're doing now is we're adding this element T that conjugates this to that. That's an HNN extension, where we're identifying two infinite cyclic groups. And so we did a free product and an HNN extension. And so the group G that we started with embeds into G prime. But if you look at this presentation, now V is in the normal closure of U. So given any group and two words that don't represent the identity, we can embed the group in a larger group so that the second non-identity element is in the normal closure of the first. If our group has solvable word problem, we can do things like enumerate all the words that don't equal the identity. And so what you do now is you just do this many times. And at the end, you've added infinitely many generators and infinitely many relations, but it's all been computable, and the group you have at the end is simple. So this embeds any group with solvable word problem into a computably presented simple group. It's very far from being a finitely presented simple group though, because you're like doing this like with basically every pair of non-identity elements, and we add new generators, you get new things that you need to do. Okay. So, okay, but that still leaves us with the Boone-Higman conjecture. So given a finitely generated group with solvable word problem, we want to know whether it embeds into a finitely presented simple group. And by the way, I wanted to mention, so Higman had this idea that algorithmic properties should all be related to embedding theorems, and this seems to be true. So for example, there's analogs of the Boone-Higman theorem that I just showed you for the order problem, the conjugacy problem, the power problem, and the subgroup membership problem in groups. So a group has solvable conjugacy problem if and only if it embeds into a certain kind of group. And actually in all these cases, there's a Boone-Higman theorem, and there's also an analog of the Boone-Higman conjecture for all of these decision problems. Okay, so I've been talking about embedding things in finitely presented simple groups. So what are some finitely presented simple groups? So at the time that Boone and Higman made their conjecture, well, so obviously there's finite simple groups, but you know, if we want infinite ones, at the time that Boone and Higman made their conjecture, there were not a lot of finitely presented simple groups known. In fact, there were arguably just two. So Richard J. Thompson defined these three infinite groups in the 1960s: Thompson's group F, Thompson's group T, and Thompson's group V. These act on the interval, the circle, and the Cantor set, respectively. And they're all finitely presented. T and V turn out to be simple. So these are finitely presented simple groups, and these were the first known examples of infinite finitely presented simple groups. And the way that this works is F is a subgroup of T, and T is a subgroup of V. So if you want to embed things into finitely presented simple groups, V is your best bet. Okay. So what is V exactly? So V acts on the Cantor set by homeomorphisms. And we're going to think of the Cantor set as this infinite product space. So it's the space of all infinite binary sequences, right? And the way that this works, of course, is that the left half of the Cantor set is all the infinite binary sequences that start with 0, and the right half is all the infinite binary sequences that start with 1, and so on and so forth. Okay, and a dyadic subdivision of the Cantor set is any subdivision that you get by repeatedly cutting pieces in half in that way. So you start with like the whole Cantor set, and then you cut that in half, and then you cut one or both of those pieces in half, and then you maybe cut some of those pieces in half, and you stop after some finite stage, and that's what's called the dyadic subdivision of the Cantor set. And this corresponds to a finite set of binary prefixes with the property that every infinite binary sequence starts with exactly one of those prefixes. And so what's Thompson's group V? So what you do to make an element of Thompson's group V is you choose two dyadic subdivisions of the Cantor set with the same number of pieces. And then you choose a bijection between the domain pieces and the range pieces. And you map each domain piece linearly to the corresponding range piece. And if you draw it middle thirds this way, it's linear. What this actually means is it's a prefix replacement, right? So if you're in this piece here, your sequence starts with 1, 1, you remove the 1, 1, and you add a 0, 1 to the beginning instead. And that's the map from here to here. It's just replacing that prefix. And so any homeomorphism of the Cantor set that you can make in this way is an element of Thompson's group V. And this group V turns out to be a finitely presented simple group. And by the way, something I want to mention about simple groups. So V is finitely presented. That group turns out to be fairly robust. V being simple, simple is something that's hard to hit on the nose. It's really easy to accidentally have non-trivial normal subgroups. And so, for example, if you do the same thing, but you do it with base 3 instead of base 2, you do not get a simple group. It has a simple subgroup of finite index, but the group itself, V with 3 instead of 2, is not simple. And this is going to be a recurring problem with simple groups. It is hard to sort of get them exactly. Okay, so V is a finitely presented simple group. So what can we embed into V? So this is sort of most of the known results on what groups embed into V. Every finite group embeds into V, essentially because all the symmetric groups embed into V. Non-abelian free groups, as well as free abelian groups embed into V. If you take infinite direct sums of groups that embed into V, those always embed into V. The generalized Thompson groups, where you use n instead of 2, those all embed into V. The Houghton groups, various wreath products, and as a result, various solvable groups embed into V. Q mod Z, and some other wreath products and and free products embedded in V. So that's pretty good. It has a lot of different subgroups, right? But this list is by no means, right, all finitely presented groups with solvable word problems, right? In fact, you can probably think of lots of finitely presented groups with solvable word problem that are not on this list. And this list, I guess I would say that it's expected to be fairly comprehensive. So if you know a prominent example of a finitely presented group and you don't already see it here, I think it's probably not going to go inside of V. So V is not going to do it for us. Okay. And so here's a specific example of a group that's not going to go inside of V. So there's this group called Grigorchik's group. So this was defined by Grigorchik in 1979. It's a certain group of automorphisms of an infinite binary tree. So take an infinite rooted binary tree, and it's a certain finitely generated subgroup of the automorphism group of this tree. And this is a pretty famous group. Grigorchik proved a couple of really cool things about this group. So first off, this was the first known example of a group that has intermediate volume growth, which solves a problem of Milnor. So intermediate volume growth is that if you look at the ball of radius n in the group, which is to say, all the elements that can be expressed as words of length n or less, the number of such elements grows faster than any polynomial, but slower than an exponential function. And so Grigorchik showed that, and we now have some very, very specific information about how quickly that grows. And then the other neat thing about Grigorchik's group is that it's a solution to the Burnside problem, which is to say, Grigorchik's group is an infinite, finitely generated group where every element has finite order. And it turns out that that makes it hard to embed into V. So Rover proved that if you have a solution to the Burnside problem, it can never embed into V. In fact, every finitely generated torsion subgroup of V is finite. So Grigorchik's group is not going to embed into V. But Grigorchik's group is finitely generated, and it has a solvable word problem because it's automorphisms of the tree. And in fact, it's some very nice automorphisms of the tree. You can describe the automorphisms by what are called finite state automata. Using those finite state automata, you get a very easy solution to the word problem in Grigorchik's group. I mean, basically, you just have to take an element of Grigorchik's group and see whether it acts trivially on the tree. So, does this embed into a finitely presented simple group? And here's something to observe about it. So it acts on the infinite binary tree, and the boundary at infinity of this tree is just the Cantor set. And so what that means is that Grigorchik's group acts by homeomorphisms on that Cantor set. And so what Rover proved is that if you just take the group generated by Thompson's group V and the Grigorchik group, that's actually a finitely presented simple group. And this was, I think, a very surprising result. So first off, as I said, it's pretty hard to actually get simple groups. It's hard to hit simplicity on the nose. And so it's really kind of surprising and mysterious that the group generated by these two groups would be simple. It's also a bit surprising that the group generated by V and Grigorchik's group would be finitely presented, because Grigorchik's group is not finitely presented. But somehow, when you add V into the mix, it makes it finitely presented. So this gives an embedding of Grigorchik's group into a finitely presented simple group. And by the way, this can all be generalized. So Grigorchik's group is one of a family of groups that act on, in general, a D-ary rooted tree. These are called self-similar groups. And Gregorchik's group has a strong property that is what's called contracting, so that all the automata have the same sort of finite nucleus of states. And so Nekrashevich proved that if you actually have any contracting self-similar group and you throw in the D-airy copy of V, that's actually always finitely presented. Unfortunately, it's not always simple. Sometimes it is. Nekrashevich gave necessary and sufficient conditions for that to be simple, but it's not always simple. So, so this theorem only extends to some contracting self-similar groups. Okay, so we're going to need some more finitely presented simple groups. So I'm going to tell you a little bit about some groups defined by Matt Bryn. And so what these are is, so there's this group called 2V, and it acts on something called the Cantor square. So the Cantor square is the Cantor set crossed with the Cantor set, which is of course homeomorphic to the Cantor set, but it's going to help us to think of it as a square. And what we're going to do with this is we're going to do dyadic subdivisions of it. So you can cut the Cantor square in half, and you can cut either vertically or horizontally. And then you can cut one or both of those in half, and so on and so forth. And any partition you obtain in that fashion is called a dyadic subdivision of the Cantor square. And an element of 2V is you take two dyadic subdivisions of the Cantor square with the same number of pieces, and you choose a bijection between the pieces, in this case represented by the colors. And then each piece in the domain, you map to the corresponding piece in the range just by stretching vertically and horizontally. So this is an element of this group 2B. And instead of drawing pictures like this, it's a lot easier to draw pictures like that. Yeah. Okay. And so Bryn proved that this group 2V is in fact finitely presented and simple. Actually, you don't have to stick with 2, so you can take the product of 3 copies of the Cantor set, that's the Cantor cube, and so on and so forth. So you get this family of groups NV, where 1V is just Thompson's group V. And Bryn proved that these are all finitely presented and simple. So this is a nice infinite family of finitely presented simple groups. And by the way, these groups are super interesting. So just as an aside, these groups NV have also some very interesting algorithmic properties. They have lots of, the word problem is solvable because they're just groups of homeomorphisms. You just check if something's the identity now. But basically everything else is unsolvable in these groups, including the conjugacy problem. And as far as I know, 2V is the first group that has sort of appeared and people have been studying it on its own, and it later turned out to have unsolvable conjugacy problem. Right, lots of groups have been kind of constructed to have unsolvable conjugacy problem, and people have found like big families of groups where you can find unsolvable conjugacy problem in one of them, but this is a specific group that was not introduced for its algorithmic properties. It was later found to have unsolvable conjugacy problem, and as far as I know, it's the first finitely presented group of that form. Yeah.
It's clear that all these groups are different.
It is true that they're all different. It is not clear, but it is true. Okay, and so what can you get inside of these groups? Well, in 2016, myself and Colin Blake and Francesco Matucci proved that you can embed every right-angled Artman group into one of these groups. And actually, it's since been proven that in fact you can get every right-angled Artman group into just 2V. And it's a property of these groups that if you can get right-angled Artman groups in, also anything that virtually embeds into a right-angled Artman group, so anything that has a finite index subgroup that embeds into a right-angled Artman group is also going to embed into 2V. And it turns out there's a huge class of groups that are known to virtually embed into right-angled Artman groups. There's these things called special cube complexes, and fundamental groups of special cube complexes virtually embed into right-angled Artman groups. These are virtually special groups. So there's this big list of groups that are known to virtually embed into right-angled Artin groups. And so now these all go into 2V, right? And so this is sort of major progress. This is a bunch of groups that we care about now that are embedding into 2V. So graph braid groups, limit groups, all finitely generated Coxeter groups embed into 2V, and a bunch of classes of hyperbolic groups and things like that embed into 2V.
Wait, you saying because they embed into right-angled Artin groups, or because they embed into?
So these all virtually embed into right-angled Artin groups, and then it follows from that they embed into 2V. Yeah, and so these all embed into now finally presented simple groups. Yeah,
Those groups are different, but may accuse that MV with large M embeds into MV with small m.
Yeah, it is known that MV embeds into NV if and only if M is less than or equal to M. But that's a recent result. That's from like last year or something. Okay, countable abelian groups. So I mentioned at the beginning that it's interesting just finding finitely presented groups that contain countable abelian groups, let alone finitely presented simple groups. There's this old problem of Higman to find an explicit and natural example of a finitely presented group that contains Q. And this was a Kuroka notebook problem. This was submitted to the Kuroka notebook in 1999 by Martin Breitzen and Pierre de la Harpe. Breitzen also talks about it in his Princeton Companion to Mathematics essay on combinatorial and geometric group theory. But we have found a solution to this problem. So there's this group T bar, which is essentially it's the lift of Thompson's group T to the real line, and this contains Q. And this group T bar is a very nice finitely presented group. There's a presentation for it that has 2 generators and 4 relations. And what is this group T bar exactly? So it's based on Thompson's group T. Thompson's group T is a certain group of homeomorphisms of a circle. Basically, you take a circle and you do dyadic subdivisions of the domain and range. And then you map each domain piece to a corresponding range piece linearly. But it has to be a homeomorphism. So you have to maintain the circular order of the pieces. And so that's what's called Thompson's group T. And a lift of an element of Thompson's group T. So an element of Thompson's group T is acting on the circle. A lift is just any homeomorphism of the real line that makes this diagram commute, where this vertical map is the covering map. So for example, for this element here, here's a picture of a lift of this element on the real line. And so there are these piecewise linear homeomorphisms, and they're kind of periodic as you go to the left and to the right. And T bar is just all of the lifts of all of the elements of T. And that turns out to be a finitely presented simple group, so finitely presented group. It's not simple. And T was in fact already known to contain Q mod Z. And it's not hard to show that T bar then in fact contains Q. And actually what you do is T bar contains the translation by 1 unit to the right. That's a lift of the identity element. And it's not hard to show that that element has a square root. And then it's not hard to show that that square root has a cube root. And then it's not hard to show that that cube root has a 4th root, and so on and so forth. Okay, but so T bar is finally presented. So that solves Higman's problem. You have a finally presented group that contains Q. T bar is not simple though. But just recently, we have found a finally presented simple group that in fact contains all countable abelian groups. So for lots of countable abelian groups, this is sort of the first explicit example of a finally presented group that contains it. But in fact, it's also a simple group. So every countable abelian group embeds into a finally presented simple group. And here's how we do this. So T bar acts on the real line. So the first thing we do is we sort of change that action so that it's acting on the Cantor set instead. You take add plus and minus infinity to the real line so that it's a closed interval, and then you take a quotient map from the Cantor set to the closed interval, and you get an action of T bar on the Cantor set. And so now T bar is acting on the Cantor set, and then you just make a group generated by T bar and Thompson's group V. And then we prove that the group generated by T bar and Thompson's group V is in fact finitely presented and simple. And this group also contains, so T bar contains Q. This group turns out to contain an infinite direct sum of copies of Q, plus an infinite direct sum of copies of Q mod Z, which was already in V. And every countable abelian group embeds into this. And so this is a finitely presented simple group that contains every countable abelian group.
Is it type F infinity?
Yes.
Oh, okay, good.
Okay, so I want to talk once more about a few more finitely presented simple groups that we're going to put things inside of. So we're going to make what are called twisted versions of Briggs groups. So the simplest example of this is you can make what's called twisted 2V. So twisted 2V is exactly like 2V, except that so remember these are Cantor squares. When you're mapping a domain rectangle to a range rectangle, you are allowed to either map it in the standard way, or you are allowed to first flip it across the diagonal, right? So switching the X and Y coordinates, right? And then mapping it. And so for every rectangle, you can do one or the other. So here we're not flipping this rectangle here, the T. And so the group of all of these is what we call twisted 2V. And in general, if you have NV, you can make a twisted version of NV. And the way you want to do this, so you can choose any group of permutations of the N coordinates, right? And then whenever you have a piece over here, you're allowed to permute its coordinates using one of those permutations, and before you map it over here. And so for any group of permutations of a finite set, you get a twisted NV. And there's no reason the set needs to be finite. So if you have an infinite set, you can make an infinite dimensional Cantor cube whose coordinates are in one-to-one correspondence with the elements of your infinite set. And then if you have a group of permutations of that infinite set, you can cut your infinite dimensional Cantor cube into finitely many pieces and twist the pieces using elements of that permutation group. And you get what's called a twisted omega. And kind of neat, so these twisted omega V's are first off always simple. And it turns out that they're finitely generated as long as the action of G on your set is transitive. And so just an aside, we use this to prove that every finitely generated group embeds isometrically into a finitely generated simple group. You just take the action of the group on itself, and you make the twisted omega V corresponding to that action. And that's a finitely generated simple group, and the group itself embeds just by twisting the whole cube using elements of the group. So that's finitely generated simple groups. You can also get these to be finitely presented. The requirements for these groups to be kind of finitely presented are kind of technical. You have to start with a finitely presented group. It needs to be acting on a set, and that action needs to be have a high amount of transitivity. Highly transitive is for every set of n elements, or for every n tuple of distinct elements, you can take it to any other n tuple of distinct elements. Actually, it suffices for the action. Ordered or unordered? Ordered, but actually it suffices for the action to be oligomorphic. So there's finitely many orbits on n tuples is fine. And you also need stabilizers of finite subsets to be, actually it suffices for them to just be finitely generated. Matt proved that recently. And as long as these conditions are true, then the twisted omega V turns out to be a finitely presented simple group. And this is good for lots of things. So, because it turns out that there's a bunch of groups that satisfy things like this. For example, the action of Thompson's group V on the dyadic points in the Kenner set satisfies all of these conditions. It's a highly transitive action, and stabilizers are well behaved. But sort of any group that's sort of Thompson-like also satisfies this. And for example, these groups that Nekrashevich made from contracting self-similar groups, they all satisfy these conditions. So if you take any contracting self-similar group acting on a D-ary tree, and you take the group generated by it and the corresponding Thompson group, that makes a group that satisfies these conditions. And so it embeds into the corresponding twisted omega V. And so this theorem gives that all contracting self-similar groups embed into finitely presented simple groups. Okay, so just in the last few minutes, this is the new theorem. This is not written up yet, but in fact, we've proven that every hyperbolic group embeds into a finitely presented simple group. So hyperbolic groups, of course, being these groups whose kilographs satisfy a delta thin triangle condition, right? And in some sense, most finitely presented groups are hyperbolic. So how does this work? So what we do is we look at what's called the Hora function boundary of a hyperbolic group. So this is not the usual Gromov boundary of a hyperbolic group. This is a different kind of boundary, also defined by Gromov. And it's very different from the Gromov boundary. It's always for a group totally disconnected. It's a totally disconnected space. Think of it as like a Kenner set of some kind. It depends on the generating set that you use for your group. But anyway, so this group has a Hora function boundary. And so what we do is we consider all homeomorphisms of the Hora function boundary that piecewise agree with elements of the group G. So you're allowed to cut the Hora function boundary into finitely many Clopin sets. And then on each Clopin set, you have to do an element of your hyperbolic group.
Is it just a full group of the?
Yeah, this is the topological full group of the tau group weight of germs of the action of G on its Hora function boundary. Yeah. And that group turns out to have the properties that you need. So first off, we prove that it's finitely presented. And it's very Thompson-like. So it's highly transitive. If you pick an orbit, it'll be highly transitive on the orbit. The stabilizers will be finitely generated. And so it follows that it embeds into one of these twisted omega V's. I'm just about out of time, but I do want to say, so why does this turn out to be finitely presented? That's where most of the difficulty of the proof is. What we show is that the action of the hyperbolic group on its Hora function boundary can be described by finite asynchronous automata. So these are, so elements of contracting self-similar groups are also defined by finite automata, but those automata are always synchronous, where for every time you take an input letter, you output exactly one letter. There's a generalization of this called asynchronous automata, where every time you input a letter, you're allowed to output any finite number of letters. And we show that, that the hyperbolic group G, and hence this group here, acts on the function boundary with respect to a certain symbolic encoding by finite state asynchronous automata, and moreover, that action is contracting in the sense of a contracting self-similar group. And then following Nekrashevich's proof that contracting self-similar groups always give finitely presented Nekrashevich groups, this group here turns out to be finitely presented for essentially the same reason. And then it embeds into a finitely presented simple group. Okay.
Questions, either on Zoom. So if you're on Zoom and would like to ask a question, you can just unmute yourself and we can hear you in the room. And if anyone in the room has a question.
I have several questions, but maybe first the questions in the room.
Could you re-explain why these things? It's really interesting to me that things coming from full groups are finally presented. So you're saying they're finally presented because you can represent them via some slightly modified automaton?
Why does this turn out to be finally presented?
Yeah.
So so we make so first we assign, so we make a tree. This is a fairly regular tree whose leaves are the Hoare function boundary. And so this gives us symbolic encoding of points in the Hoare function boundary. And then we prove that the action on that symbolic encoding is by asynchronous automata. And that proof is very involved and has lots of like deltas in it and stuff, right? Sure. But it's but you're essentially proving that if you look at how an element of the group is mapping a certain piece of the Hoare function boundary to a certain other piece of the Hoare function boundary, there's only finitely many different ways that can look on each piece. And so that turns out to be true for hyperbolic groups. And that's why you get the encoding by asynchronous automata. So sort of the different ways that it can look are the states that you need.
Sorry, I'm sure this is my question. So why doesn't asynchronous automata yield
finally presented?
Exactly.
So it needs to be not only asynchronous automata, but it needs to be contracting.
Yeah.
So there's a finite nucleus of states, right? And then the generators for your group are the generators for the Thompson group, the associated Thompson group, plus you need one generator for each of those finite nucleus of states. And then you need relations that tell you things like, if you have a state in the nucleus, what happens when it takes different input letters, and things like that. So the finite nucleus of states has a finite amount of information associated with it that sort of proves that it's a nucleus. And you can translate those sort of directly to relations in the group. So I don't know. Does that answer your question?
Yeah.
All right, questions on Zoom?
May I ask some of my questions? I don't know if you hear me good. Rachel, is it okay?
Yeah, I can hear you.
Yes, we can hear you well.
Yes, so I would like to ask, first of all, thank you for a very interesting talk. So I have several questions. First, I wanted to ask a very small question, maybe I didn't follow when you were embedding Q in T-bar. Could you explain again why Q rational numbers are embedded in T-bar?
Oh, so the elements of T-bar are certain piecewise linear homeomorphisms of the real line. The conditions are, they have to be sort of Thompson-like, where all the slopes are powers of 2 and the breakpoints are dyadic rationals. And then they have to be periodic in the sense that f of x plus 1 is equal to f of x plus 1 for all x. And so all we did, so that's a sort of extrinsic description of T-bar as a group of homeomorphisms of the real line. And all we did is we showed that if you take the translation by 1, that you can make a homeomorphism that's a square root of that. And then you can take that square root and you can make a homeomorphism that's a cube root of that. We just constructed these homeomorphisms directly. And it's really not very difficult. Our paper is like 5 pages.
Thank you. And then I would like to ask some other questions. So you mentioning some groups, for example, Guba-Sapir result about Reef products and some other groups like Rigacho groups. And I wanted to ask about the question embedding into finally represented simple groups. What is known, if you like the group to be not too large? For example, for some solvable examples or some other groups of intermediate growth, can you embed them into an amenable simple group, maybe, which is finally presented?
Right. So these are known now, right? Finally presented simple amenable Yeah, and I think these are among the Nekrashevich groups, is these examples of simple finitely presented amenable groups, I believe. But I'm not trying embedding anything into them, so I really don't know. They can't be quite
I wonder if somebody maybe in the audience knows.
Anna, doesn't Nicola have a paper where he embeds the Grigorchuk group into, I don't think all sub-exponential group, but particularly Grigorchuk group, into the full group of some subshift, right? Which he, I think, into the conjugator. I think he might have a paper where he embeds it into an amenable simple group. Not finally presented, of course, but
yeah, anything that contains some subscript V is going to be non-amenable.
Right.
Yeah.
So So the answer is that I know very little about the amenable finitely presented simple groups.
So I was wondering, even in the case of solvable groups, like in the case of Reeve products, not so clear, is it?
Yeah, so actually for solvable groups, the only groups that I know how to embed are, so there's the ones that embed into V, and then there's a few more Reeve products that are known to embed into the NVs, and then I know how to do, I think I know how to do solvable Baumsog solitaire groups. But aside from that, I have no idea how to embed solvable groups into finitely presented simple groups.
Thank you. I also have some other questions, but I see there is a question in chat, I think, so maybe first.
Can we say something about the difference and similarity between twists of 1V, 2V, and NV? It seems that twists of 1V must be related to permutations, 2V must be related to braids. Is there a good reason for concentrating on the first two? So, right, so we don't concentrate on the first two. All of these embeddings were into twisted omega V's. But what we're calling twists is just permuting coordinates. So you can't, so by our definition, you can't twist V. There's things that you could do to V, like you could consider taking V and being allowed to flip intervals over, right? Do a reflection of intervals. Those are an NV, but that actually turns out to give you a group that's isomorphic to V. But we don't concentrate on. What was the question again? We don't concentrate on. So we don't concentrate on 2V. In fact, we go to the infinite dimensional case very quickly. But all of these finite dimensional twisted 2Vs, twisted NVs should be interesting groups as well. For embedding purposes, it has to go up to infinite dimensions, but like classifying these groups up to isomorphism is an open problem. Does that answer the question?
So can I ask a question?
Sure.
So for your last case, at the end, this VG for hyperbolic case, at the end, what exactly does VG act on? Because you said highly sensitive on some orbit, I suppose is not the full Hall function boundary. And that is like Cantor said.
So the action needs to be highly transitive. So it's not highly transitive on the whole Cantor set, but what you do is you take like one generic point in the Hall function boundary, and you look at the orbit of that point on VG, under VG.
Okay.
Yeah, and then that action will be highly transitive.
So can your strategy be summarized as you first found your group acts somehow on some kind of Cantor set, and then you sort of trying to build a piecewise linear version of this action?
Yeah, well, it's not piecewise linear, it's piecewise G. It's so whenever you have a group acting, you can just look on a Cantor set, you can just make a new group, which is all the homeomorphisms that piecewise agree with the given group. Yeah.
So potentially you could work for other classes of groups, I suppose. Yeah.
Yeah, and in fact, every group has a Hall function boundary. That's not a definition that's exclusive to hyperbolic groups, but then the trick is getting this group of piecewise G things that you make to be finally presented.
Yeah, I think so. Matt asked question. So I heard a talk by Matt before, so he's asking for automorphism of free groups and mapping class group. So
yeah. So yeah, so it's open for both mapping class groups and braid groups, whether they embed into finally presented simple groups.
It just was a comment from Matt about this.
Let's see. So here's this slide that I have on mapping class groups. So I think that this is sort of the best strategy that might work for mapping class groups. So mapping class groups act on the boundary of type Mueller space, PMF, and it acts by what's called piecewise integral projective maps. And when you're acting on just a circle by piecewise integral projective maps, that gives you exactly Thompson's root T. And it's an open question due to Thurston, whether for higher dimensional spheres, whether the group of piecewise integral projective homeomorphisms is even finitely generated is open. But in the n=1 case, you get Thompson's root T, so it's a finitely presented simple group. And so I think there's a good chance that these higher dimensional PFP groups are also finitely presented simple groups. And then that would resolve the embedding of mapping class groups. But yeah, but this has been open for a while. So yeah.
Thanks.
You're welcome.
Any other questions? All right, let's thank the speaker again.
May I ask the last question? So I had a problem.
Yes, go ahead, Anna.
Just a very last question in relation with your result about hyperbolic groups. So what about residually finite groups? If you have a residually finite group, should it be embeddable in finitely presented simple one?
So that's a good question. So first of all, these embeddings of hyperbolic groups into these groups acting on the Hoare function boundary, those groups are kind of like self-similar groups, but they don't act in a level preserving way on the tree. And so for that, you don't get residually finite. So we don't think that the embedding that we have is going to help with showing that hyperbolic groups are residually finite. It's an interesting question whether arbitrary residually finite groups might be embeddable. I haven't thought about that.
I mean, if it's open for braid groups, then it's wide open, I'd say. Right.
But
yeah,
so
I mean,
can you just take in its profile completion, which is also, is it a Cantor set? It's a locally compact group, right? And totally disconnected.
Yeah. So whenever you have right, every group acts on its profinite completion.
But it won't be contracting in the way you want it to be present.
I guess it might be for a residually finite group. I don't know. That's.
I mean, you can, for a residually finite group, you can even just build the tree of like its residual quotients basically, but it's not going to be contracting in the way you want it to.
Yeah. So right, you need the tree to somehow be self-similar. Like if you look at subtrees dangling off different nodes, there needs to be finitely any isomorphism types of those subtrees.
But even like a residually P group, I don't think it will be enough. No.
I don't know, maybe. I haven't thought about it.
Okay.
Yeah, the contracting property is ridiculously important. We tried doing the similar thing for the Loda-Moore group, and it completely breaks down and doesn't work. And the failure to be contracting is the problem. Yeah.
Okay, good.
All right, thank you.
All right, so the next talk is in, let's say, 1 minute, yeah? I think I saw Mark there, so he should be.
Yeah.